Okay, good. Okay, so I'm going to draw a picture, a diagram of a hydrogen atom to start with. Okay, so in the middle, I've got that, and the key here is the dark things are protons. Okay, so I've got one proton, and around the outside, and I'm just going to draw a diagram. This is not really what it looks like. And the small little dot is an electron. Actually, I might do it as a cross, but it's pretty easy to see. Okay, so that's a diagram. So it just represents, in an easy to picture way, what a hydrogen atom would look like. So this is hydrogen. Okay. And we give it the symbol, capital H, 1 and 1. Okay. Now, we'll figure out what these numbers mean before too long. But I just want to focus on the structure here, so the diagram, what it looks like. Okay. So here's helium. So we've got helium has 2 protons. And it also has 2 other particles in its nucleus. They're called neutrons. Okay. Okay, so we've got 2 protons, 2 neutrons, and we also have, in the shell around it, 2 electrons now. Okay. So we've got one shell for the hydrogen, we've got one shell with 1 proton and 1 electron. In helium we have one shell with 2 electrons in it, and there's 2 protons and 2 neutrons. So that's helium. And that's how we write the symbol for helium. Okay. Now, I should actually specify here, when we're talking about atomic physics, which is what we're sort of getting into now, this is how you write it. When you're talking chemistry, you don't need to worry about the numbers. They're here. Okay. So these 2 numbers here, so that number there is what we call the atomic number, and it is the number of protons. Okay. Now, for every specific type of atom, so every hydrogen atom has only 1 proton. Okay. That's what makes it hydrogen, the fact that there's 1 proton. Every helium has 2 protons. Okay. And so you can see here, this is the atomic number. This number here is the mass number. And the mass number is basically what is the, if we were to think about the particles that would make up the nucleus, so in this case we've got 1 proton, but in the helium we've got 2 protons and 2 neutrons, so there are 4 what we call nucleons in the nucleus there. Okay? And they've all got, they're not equal mass, but they're pretty much the same mass. And so we approximate that as being a mass of 4 atomic mass units, AMU. Okay? So this mass here, mass number, tells us how many nucleons we have. You'll notice here that the number of electrons is equal to the number of protons. So we've got 2, for the hydrogen we've got 1 electron and 1 proton. And this is for a neutral hydrogen atom. And for a neutral helium atom, we've got 2 protons in the nucleus and 2 electrons in the shells outside. So to be neutral, the number of electrons must be the same as the number of protons. You can sort of think of it as being like a scales of positives and negatives. So if you've got equal number of positives and negatives, then they're going to balance out, and overall the charge is 0. If you were to somehow remove one of these electrons, you would have one more proton, and therefore you would have a charge overall of the atom of +1. Okay, so that's what we call an ion. Okay, so there's hydrogen and helium. And if you were to look at your periodic table, so we can just use the one that's on the wall up here for the moment, you'll notice, let's find hydrogen and helium on there. So you'll see hydrogen is the very top left, and helium is the very top right. Okay? But the main point here that I'm trying to show you here is that they're in the same row. Okay? So the rows that go from left to right, we call that the period. Okay? So the period, they're both in the first period. Okay? So they're both in the first period. Okay. If we were to go to the next largest atom, so we've got an atomic mass of 1 for hydrogen, an atomic mass of 2 for helium, so the next largest atom would have an atomic mass of 3. That's terrible. Okay, so the atomic mass of 3, well, what does that tell us about it? If it's got an atomic, sorry, not atomic mass, the atomic number of 3, what does that tell us about what's in the nucleus? Olivia? 3 protons, haven't we? Okay, so this is for lithium. Okay, and we've got 3 protons in the middle. Okay, and for most lithium atoms, there would also be 3 neutrons. Okay. Now I've only drawn it in 2 dimensions because this is a diagram after all. In reality, they are packed together in 3 dimensions. Okay. You kind of think of the protons and the neutrons as being like little balls. Okay, but they are really, really little. All right, really, really small. Like, not quite sure what the diameter of a proton is off the top of my head, but it is like something like 10 to the minus 18 metres or something like that. So it's really, really small. So we've got 3 protons and 3 neutrons in this lithium atom. And how many electrons would we have for a neutral? We would have 3. Okay. But in physics, or in nature, there's something about this first electron shell here, and it can only hold 2. Alright, so we only have 2 electrons in that first shell, so we need to have another shell to hold that 3rd electron. Okay? So now we've got lithium, which has a symbol Li, atomic number of 3, and this one has an atomic mass of 6. Okay, so we've got 3 protons, and add to that 3 neutrons gives us 6 nucleons. So 3 protons, so atomic number. So all lithium atoms have 3 protons, but this particular atom has 3 neutrons, so that therefore there are 6 nucleons. And it's neutrally charged, so it's got 3 electrons to balance the 3 protons. And in order for that to happen, we need to have 2 in that first shell, and then a second shell to contain the 3rd electron. Okay? So the next one would be atomic mass of 4. And just for simplicity, I'm going to have 4 neutrons in there as well. So that would be an atomic mass of 8. 4 protons plus 4 neutrons gives me 8, an atomic mass of 8. So what would be the atomic species that has atomic number of 4? Anybody? Be beryllium. Okay, so beryllium. Okay, and has a symbol Be. Okay, so we can identify the atomic species simply by looking at the number of protons we have in a nucleus. Let's just draw the diagram for this. So how many protons would I have in the nucleus there? 4, okay. So I just draw 4 protons. And with my atomic mass of 8, that means how many of the nucleons are neutrons? Another 4, isn't it? Okay. So I'm just going to draw 4 neutrons there. And for a neutral atom, how many electrons would we have? 4. Okay. So we would have how many in the first shell? We can only hold 2. And so therefore there must be the remaining 2 in the second shell. Okay? Now, you're probably wondering, why did I draw the next electron there instead of down here? Well, after all, it's a diagram. And in my head, the way it works, it's not actually what happens, but the way that I can systematically fill up these electron shells is by going clockwise. And I already know something in advance here, which we're about to figure out. Okay, it might make sense when I explain it. Okay, so how many, when we had helium and hydrogen and helium, we could only hold 2 electrons in that first shell. Okay. After that, we had to go to another shell, so we had to have more than one shell, 2 shells. And if you have a look at the periodic table, we've got 2 atoms, or 2 different species of atoms, in the first period there, so hydrogen and helium. When we got to lithium, we went to a new row. Okay? So that new row there was because we've now gone to a new shell for a neutral atom. Okay? So the number of shells here is equal to the period that it's in. Okay? So if I were to ask you sodium, which is right below lithium there, that's in period 3, how many electron shells would a neutral sodium atom have? It would be 3. Okay? Potassium would be 4, and so on. So any one of those atoms, I could ask you how many electron shells would a neutral atom have, and you could tell me just by counting how many rows down you are. Okay? So that's the first sort of little snippet of information. We're going to write that up on this board. So the number of electron shells in a neutral atom is the same as the period number. Okay, so to turn to the camera, the number of electron shells in a neutral atom is the same as the period number. So if I have 3 shells, so for example magnesium has 3 shells in a neutral atom, well that's in the 3rd period. Phosphorus also has 3 shells. All right. Mercury, that'll be, well that's in the 6th period, so mercury, a neutral mercury atom, would have 6 shells. All right. So we can see here that there's a bit of a pattern forming. As you go up the periodic table, you'll notice that every time we fill up a shell, we have to go to the next shell, and so and it tells us where the period is. So if you look at the periodic table, you can work out how many shells it would have. The first shell could only hold 2, and there are only 2 atoms in that first period. How many atoms in the second period? We've got 2 on the left there, and then a bit of a gap, and then 6 on the right, so that makes 8 atoms. So how many electrons do you think that second shell can hold? It's going to be 8. Okay, so let's draw a diagram for neon now. I'm going to skip a few, because I've done lithium and beryllium. I'm going to skip a few and do neon. Okay, so I'm going to draw a neon atom. Okay, so who can tell me how many protons does neon have? Any atom of neon? 10, isn't it? Okay, if you have a look on the that periodic table, it's got actually the atomic number to the top right. Your formula sheet, which I don't have one in front of me, has a on your formula sheet as well, and I think it's actually at the bottom, maybe? Or is it the top? Yeah, okay. So the atomic number is at the top on your formula sheet. Okay. Try not to get that confused as to telling you where you need to write the mass and the atomic number when we're writing the symbol in the atomic physics part. Okay. And the symbol for neon is Ne. Okay, so we know it's got an atomic number of 10. Who could tell me what the mass number on the formula sheet says for neon? 20, was it? Oh, 20.18. So it's not a whole number. Okay. Oh, that's interesting. Well, maybe we'll explore that later. So I'm going to actually make this particular one have an atomic mass of 21. Okay. So if it's got an atomic mass of 21, we've got 10 protons. How many neutrons must we have? Must have 11. Because the number of protons plus the number of neutrons is equal to the atomic mass. Okay, so this is going to be a little bit messy because I've got to draw 21 protons and neutrons in here. Alright, I might draw them.
Just do it times by, how many there's in here.
I'm just going to draw a whole bunch of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. One more. So there's my nucleus. It's a whole lot of protons and neutrons all packed together in a tiny little spot. And how many electron shells do we have for neon? So which period is it in? It's in the second period, so it must have 2 shells. So let's draw the first one. And that's going to be full with 2 electrons. And draw the second one. Now here's a hint as to why I started when I drew the beryllium. I did a cross here, and then I did a cross here. Because what I'm going to do is I'm going to fill it up in the sort of the north, east, south, west sort of points first, just with one cross. And then I'm going to do the same again until I reach the number of electrons to make up the neutral atom. So in this case, we're going to have 10 electrons in total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's my last one. Okay? And that is a full shell. Okay? So the first shell only has 2 electrons in it, or can only have 2 electrons in it. That's the maximum number of electrons. The second shell can have 8. How many do you reckon the third shell can have? 8 as well. So if you look at the third period, there's only 8 elements there. And the fourth shell, 18, isn't it? Okay, so we're going all the way along. Okay, the fourth, fifth shell have 18. The sixth and seventh shell, right, we don't. This is not actually testable, but just show you how it works. Notice how there's a gap between beryllium and boron there in the second period. So the second and third period have a bit of a gap there, and then there's another whole bunch of atoms sort of stacked, squished in between. Well, if you would actually draw the periodic table, continue on in this, the 6th and the 7th periods, it'd sort of be the same, but with what we call the lanthanides and actinides, which is this extra bit at the bottom, wedged in between there. Okay, so it'd be another big gap between carbon and scandium, and strontium and yttrium. So, sorry, not carbon, calcium and scandium. There'd be another gap there, and below that, then there would be the lanthanide and actinides. But in order to keep it nice and compact, they draw them in a separate bit below. Okay. Now, and you can work out how many would be in the 6th and 7th shell by counting. You get 18 plus another 2, 4, 6, 8, 10, 12, 14. 14, because the lanterns count, sort of shown twice there. Another 14. Okay, so 18 plus 14 is 32. So there'll be 32 electrons in those shells in 6 and 7. Okay, and for those of you going to do chemistry next year, you'll actually learn that there are subshells. So in the, well, actually we call them an orbital. So that's an orbital. That's actually made up of 2 shells. This second shell, the second orbital here is made up of 2 shells, and so on. Okay, don't need to worry about that for this course. The thing that you do need to know is that when you go up the atomic series, or up through the periodic table, that as you increase the number of electrons in those outer shells, when you exceed that, you have to go to another shell. So the next atom after neon is sodium. Okay, and I can actually do this quite easily. I'm just going to cheat. So it's sodium. Okay, now we're going to do sodium. Okay, and sodium has an atomic number of 11. Okay, so it's the next one after neon. And I'm going to pick an atomic mass of 23. So I need 1 extra proton in here and 2 more neutrons. Okay, so there's my nucleus. And let's make this a neutral atom as well. So I need 11 electrons in total. But my second electron shell is full. So I need to add another one. Okay, so that would be sodium. So very similar to the neon, except we just got 1 extra electron on the outer shell there. So 1 more electron than neon, and it has to be in its own shell because we're full. All the other shells are full, and well, the nucleus is going to be a little bit bigger and a little bit heavier. Okay. Now, we can ionise a sodium atom. So there's 2 different ways we can ionise something. We can add electrons to it, or we can take them away. Now, what do you think is going to be easier, adding electrons to, and let's add it so it's a full shell. So if we wanted to add it to be a full shell, we'd need 8 electrons in that 3rd shell there. So is it going to be easy to find an extra 7 electrons and make them stick to the nucleus? Or would it be easier to get rid of one, like steal it? It'd be more easy to take away that electron. Okay? So we're going to ionise this sodium atom now. Okay? And so now we've got 11 protons, but only 2 plus 8, 10 electrons. And so overall, what is going to be the charge of that? So it's the number of positives, subtract the number of negatives. It's going to be a positive 1, isn't it? Okay, so that is what a sodium plus 1 sodium ion would look like. And what do we notice about its electron configuration? What's it the same as? Neon. Okay? So a sodium ion has same electron configuration as neon. Or sodium plus, the plus one sodium ion has the same electron configuration as neon. Okay? Now there's something in nature that says that those electron shells, they prefer to be completely full. Okay? So this, when we had the sodium, neutral sodium atom there, it really doesn't like having that one electron all on its own in its shell. It wants to, if it can, either fill up that shell or get rid of it completely. And it's going to do whichever is energetically favourable, as in what's the easiest to do. You know, nature's pretty lazy. It likes to do what takes the least amount of energy to do. And in this case, the least amount of energy would be to get rid of that extra electron. Okay? But something has to take that electron. And so I'm going to look at let's look at a fluorine atom now, and I'll draw that on this here. Okay, so we've got a sodium ion, and let's draw a fluorine atom. Okay, so fluorine has an atomic number of 9. It's got the symbol F, and I'm just going to do an atomic mass of 18. Okay. Now, you're probably wondering why am I being quite random with the atomic masses there. We'll talk about what they actually are, the difference later on, but they're called isotopes, and I could have a fluorine 19 or a sodium 22, so on. Okay, so I can have different atomic masses for the same species of atom. This is called an isotope. We'll cover that later. So we've got a fluorine atom with an atomic mass of 18. So we're going to have 9 protons. There's my 9 protons. And how many neutrons? 9. Okay? 9 plus what equals 18? 9. All right. So there's my nucleus. Bit of a mess, but reasonably you just figure out that there's protons and neutrons in there. Okay, and how many shells are we going to have? 2. It's in the second period, so it's going to be 2. The first shell, 2 electrons, it's full. The second shell, we need to get to 9, so I need 1, 2, 3, 4, 5. Let's skip this one. 6, 7. That makes it to 9. Okay, 7 plus 2 is 9.
Oh, sorry.
Okay, so I left this one as the unpaired one for a reason. Okay. Now you notice how I did draw them in pairs. Okay. So there's anyone heard of quantum stuff? Anyone heard the word quantum before? Chances are you probably heard it in the wrong context. But quantum mechanics is a branch of physics, and there are some special rules that go with that, and they're trying to sort of make them all work together. But the quantum theories work best for really, really small stuff, like atoms and electrons. Okay? And there's something called spin. There's a theory, a property called spin, and these electrons, and you don't need to know this for this, but I'd just like to give you a background. These electrons have an up and a down spin. So there's, you can sort of think of it like a top spinning clockwise and another top spinning counterclockwise. Okay? And when they pair up, that means that one's an up spin and that one's a down spin. Okay? And they do like to pair up, so in the same way that the shells like to be full. Okay, so it's an energetically favourable state for them to pair up. So that's why I've drawn the crosses in pairs like that, okay, because they do pair up. When we look at covalent bonding, this will make a lot more sense. Okay, so here's my fluorine atom. It's got 18 nucleons and 9 electrons. And is that second electron shell, is it full? No, it's not. What would I need to do to make it full? I'd need to put an extra electron in there, wouldn't I? So if I were to take an electron from something that could give away that electron and put it in there, I've now got myself a fluorine ion. And how many electrons compared to protons do I have? Right, so I've got 9 protons, but now I've got 10 electrons. So if I subtract the number of electrons from the protons, I've got a -1 because I've got more electrons. And so that's my charge. Subtract the number of electrons from the number of protons, and it gives me the overall charge of that ion. Okay? So if they're equal, so it's a neutral atom, number of protons is equal to the number of electrons, so subtracting the 2 just gives you 0. Okay, that'd be neutral. But if there's more electrons, it's going to be negatively charged. If there are fewer electrons, it's going to be a positive charge. So now what we've seen here is that if we go back to the neutral atoms, just briefly, so I'm just going to briefly go back to the neutral atoms. I'm going to draw, oh whoops, that's right. I'm going to draw the electron, the only electron in that third shell of this neutral sodium atom here, and the unpaired electron in the fluorine atom here. What happens in a chemical reaction, that electron can move. Okay? So it says, oh, I really don't like having that extra electron there. Can somebody take it away, please? And the fluorine says, oh, I really don't like having that hole where an electron should be. Can somebody give me one, please? Oh, well, it's a mutually beneficial arrangement there, isn't there? We have an extra electron and one less electron, and so they say, okay, all right, I'll take your electron. And that is a chemical reaction. The process of taking the electron from one atom and putting it on the other atom is a chemical reaction. So this would form two ions. So then we would have our sodium fluoride back again, our sodium ion and our fluoride ion, and that would be something called sodium fluoride. Okay? You probably had some in your toothpaste this morning. So, has anyone heard of fluoride before? They put fluoride in water and all sorts of stuff. Okay? So it helps your teeth. Hardens the enamel so that it doesn't corrode away too much. Okay, so that would be a chemical reaction between a sodium atom and a fluorine atom. Yep.
So do they share the electron or swap?
They swap. In this case, they swap. Okay? So, in this case, the electron is actually basically stripped away from the sodium atom. The fluorine atom takes that electron. And then, if they were dissolved in water or something, they could then go their separate ways. Okay? If they're in a crystal, so like if that was chlorine, for example, so there'd be sodium chloride, and it was dried out, so it was all solid, then they would form a crystal lattice, which is what the table salt that you see on your that you put on your porridge. That makes people squirm. I know. Seriously, you've got to try it. Okay, so that's a chemical reaction between a metal and, in this case, a non-metal. And can anyone remember what type of bond that's called?
Wait, what was the question?
Between a metal and a non-metal. Ionic, isn't it? Okay? Because it forms these ions. Okay, so there's the hint. It forms ions, so it's an ionic. All right. So now, just to summarise, the atomic number increases by 1, so that determines the number of protons in the nucleus. Okay? So, actually the other way around. The number of protons in the nucleus determines what atomic species you've got. Okay? So all hydrogen have 1 proton, all helium have 2, all lithium have 3, and so on. You can have different atomic masses, and we'll talk about that soon. The period is how many shells that atom would have for a neutral atom. Okay? So notice how I've stressed that it's a neutral atom. Because this sodium ion now only has 2 shells. Alright? But it's still in period 3. So it has to be a neutral atom for me to work out how many shells it would have. And those shells can only hold a certain number of electrons, okay, which I've tabled here. So the first shell is only 2, the second and third shell is only 8, and we don't really go much into the electron shell configurations of anything past that. Okay. So the number of electrons that can hold in that shell is equal to the number of electrons that are in each period. So the second shell can only hold 8, and so therefore the second period has only got 8 atoms in it. Okay. If I were to add another electron, I'd have to go to the next period down. And the final little bit that I'd like you to look at before we finish up: how many atoms are in? How many electrons are in this outer shell for a neutral sodium atom? This is the one, isn't it? How many atoms along from the left is the sodium atom on the periodic table? It's the first one, isn't it? Okay. All right. So the next one, magnesium, would have 2 electrons in that outer shell. And it's how many atoms from the left on in that period? 2. So I can actually just look at that periodic table and say how many electrons are in the outer shell for a neutral atom based on counting from left to right. So carbon, don't forget, you can sort of ignore that gap. Carbon would have, it's 1, 2, 3, 4 from the left. So a neutral carbon atom would have 4 electrons in the outer shell. What about, well, fluorine? Let's look at fluorine. We've got the example here. Counting from the left. It's in the second period, so we're going to start at lithium. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7.
So would carbon give or take its boiler?
That's a tricky question, that one. Carbon is a non-metal, and it's sort of halfway in between. So it can kind of give or take, but they tend to not do either. They tend to share. Okay, so they tend to share electrons with other, which is called a covalent bond, and we'll talk about covalent bonding later on. Okay, so between the really easy ones to think about are the 2 left periods on the left. 2 left columns rather. So they're called groups. So group 1 is hydrogen, lithium, sodium, potassium, so on. Group 2 would be beryllium, magnesium, and so on. Okay, and then the 2 left are the metallic ones, and they are really quite reactive. And then you look at if you look at where it says it's got 18 above it, and some periodic tables you'll see it written in Roman numerals, the 8, which would be. So fluorine is in the 7th one, so it'd be like that. So that's group 7. So group 7 is fluorine, chlorine. Well, actually, bromine's in group 17, just to be confusing. Sorry. It's really because the 7 and 8 is only for the period 2 and 3, because there's only 8 atoms in those periods. Groups. Period 4 and 5 and so on, then we go up to 17 and 18 and so on. So the Roman numerals is for groups 2 and 3, and that tells you, like the group number, that's group 7. Well, group 7 has 7 electrons, okay? And group 8 would have 8 electrons. Yeah,
Does that mean that hydrogen and helium are like 1, 2, 3, 4?
No, group hydrogen, helium. Well,
Oh, sorry.
okay. The ones on the right, I'm actually about to get to that. The ones on the right, they're a special case. Okay. So remember when I did the diagram for neon? Neon had 8 electrons in that outer shell, and that was full. Okay. So you remember what we call that group there on the right? Yeah, Olivia? They're the noble gases. Okay. Noble meaning they don't react with anything. So helium, neon, argon, krypton, and so on are the noble gases, and they have the full outer shells. Okay, and that full outer shell, remember what I said that the outer shell wants to be full, and so it'll do whatever it can. It'll give away electrons or steal electrons to get that full outer shell. But if it's already got a full outer shell, well, it's going to be pretty happy, isn't it? So it doesn't want to do anything with the electrons. It says, oh no, I'm happy here. You can take electrons or give electrons to something else. So those atoms on the very far right, the noble gases, aren't very reactive at all. Okay, so we don't really refer to them as a group because they're called the noble gases. Here. The number of spaces along from the left tells you how many electrons are in the outer shell. The number of rows down, so the period, tells you how many shells there are. Okay, and all of the internal shells in this simplistic model are full. Okay, so the first shell must be full before any electrons can go in that second shell. Okay. Now, as in all things in science, there are some exceptions to that rule, but we won't go into those in this course. Okay, so before we move on, anybody got any questions?
Can you just say again what was the field?
Okay, so I've just written up on the board here with an example to account for my very poor structure of sentence there. Wording. The number of the atomic species from the left in a particular period is equal to the number of electrons in the outer shell. So an example there would be magnesium. So if you look at where magnesium is, it's second from the left in the third period. So it has 3 shells because it's in the third period, and 2 electrons in the outer shell because it's second from the left in that period. Okay, so when we're talking about electron configurations, there is a shorthand way of doing it, of writing it. So for sodium, we've got 2 electrons, then 8 electrons, and then 1 electron. That's for a sodium atom, neutral sodium atom. And so I would write it like that. Okay, so electron configuration. Okay, I put a little, like a bracket, curly bracket, round bracket rather. 2, bracket, 8, bracket, 1. So that indicates how many electrons are in the first shell, second shell, third shell. Okay, so this would be neutral sodium. What about a sodium ion? What would be the electron configuration for a sodium ion? Must be 2 and 8. We don't have that 1 shell, do we? That's right, it's been nicked from something else. That's right. It doesn't have to be taken away necessarily by another atom. You can ionise things without having to be a chemical reaction. So static electricity is a pretty good example of that. That's an ionisation. Okay. However, in this course, let's just think of it. Okay, it's easy to think about. We've got an chemical reaction going on. Okay, so let's do some other examples of that. So let's look at carbon. Okay, so carbon, it's in the second period, so it's going to have 2 shells. So I'm going to write 2 numbers. First one's going to be full, so it's going to be 2. We're at atomic number 6. So 2 plus what equals 6? It's got to be 4. Okay, so that's when we don't have the diagram, we can still do it without having to draw a diagram, because obviously that's going to take quite a lot of time if you had to do that. Whereas we can still do it. Okay, so it might actually be easier. I'm going to leave the atomic mass blank for the moment because that's actually irrelevant for what we're talking about. So that's carbon. It's got 6 atomic number of 6, and so the sum of all these numbers must equal that. Okay. So let's look at sulfur. So what's the atomic number of sulfur? 16. Okay, and so it's in the third period, so we know there are going to be 3 shells. And that gives you a hint as to how you can do it. You can go, right, first shell, full. Second shell must be full, and that's 8. And so we've got 2 and 8, that makes 10, plus what equals 16? Must be 6. Okay? Now I'm going to throw one in the mix. We've got a sulfur ion there, sulfide ion. 2 minus. So what that means is that there are how many electrons would there be with that? There'd be 18, wouldn't there? Because we've got 2 extra electrons, or 2 more electrons than protons. So 16 plus how many minuses we've got there is what I've got in the number of electrons. So 2, first shell's full, second shell also full, and 10 plus what equals, well, that's going to be 18. So it must be 8. Okay? Now, do you reckon we can get a sulfide 3 minus ion like this? That's a good question. You reckon that one's possible? It certainly wouldn't want to be like that, would it?
That is possible.
Why is that? Yeah. So let's draw let's write down the electron configuration for this. So we've got 19 electrons now. 3 more electrons than 16 is 19. And so first shell's full, second shell's full, and well, I can't have 9 in that third shell, can I? There's no room at the end. There's seats. There's little spots for those electrons to go, and if there's no spot left because there's already an electron in it, well, I need to get put somewhere else. So it needs to have, that one's full, it needs to have be like that. And so it's unfavourable for 2 reasons. The first reason is that we don't have a full shell. Okay, that outer shell there, not full. Alright? And secondly, well, we actually have to put one in another shell. Okay, so you have to create a new, or fill a spot in a new shell, and that is going to require a lot of energy to do that. So it's going to be pretty difficult to make this ion. Not impossible, just difficult. Okay? Was that your question, Olivia?
Yeah.
Yeah. So, well, in physics, nothing is impossible. It's just a matter of how much energy you're prepared to do to make that. Okay?